We'll need this equation to analyze titrations. You've probably seen this introduced in Chem 1211, but we're going to cover them in more detail now. A titration is a procedure, often based on an acid-base neutralization reaction, for determining the concentration of a solution by allowing a carefully measured volume of said solution to react with another substance of known concentration. The point in a titration at which stoichiometrically equivalent amounts of the reactants, which are typically an acid and a base, especially in this chapter, have been mixed together, is known as the equivalence point. While you've probably seen an indicator like phenolphthalein used to monitor a titration reaction, this can be done more quantitatively by using a pH probe to measure the pH of a titration solution at each point as a function of the amount of the standard solution added. In this example, a 0.100 molar HCl solution is titrated with a solution with the same concentration of sodium hydroxide, and the pH of the solution is plotted against the volume of sodium hydroxide solution added. Let's consider the reaction at play and use it to analyze the shape and other characteristics of this graph and determine what exactly that shows us. For a simple strong acid, strong base titration, we pretty much boil down to this equation here. This is the reverse reaction of the dissociation of water, so it's so product favored that we can ignore any equilibrium effects and just assume that it proceeds to a 100% extent. And each mole of acid reacts with the same number of moles of base. Before any sodium hydroxide is added, so at 0 milliliters on the x-axis, we just have our starting 0.1 molar hydrochloric acid solution. If you calculate the pH of the solution at this point, it should be equal to 1, which is pretty much our starting point on the titration curve. As we add sodium hydroxide, some of the HCl will be neutralized, but we won't be able to neutralize all of it until we've added the right molar equivalent of our base. So between 0 and 40 milliliters of sodium hydroxide solution added, the solution remains acidic due to the remaining unneutralized hydrochloric acid. In this example, we reach our equivalence point when exactly 40.0 milliliters of sodium hydroxide solution has been added. This occurs when we've added exactly enough of the base to neutralize all of our acid without adding any excess. You can identify an equivalence point based on the sharp change in pH relative to the other portions of the graph. Also, for any monoprotic strong acid, strong base titration, the equivalence point will occur at a pH of 7. Finally, continuing to add sodium hydroxide solution after the equivalence point just results in the solution containing excess hydroxide, so the pH rises rapidly and then continues to increase. For a strong acid, strong base titration, we can calculate the pH at any point, as shown in these data points. Initially, since we're starting with a solution of hydrochloric acid, the pH is simply determined by the concentration of our acid. As we add the sodium hydroxide, but before we reach that equivalence point, the pH will be determined by the concentration of the remaining acid. This is determined not just by how many moles or millimoles of hydronium ions remain, but we also need to account for the fact that adding the sodium hydroxide solution also adds to the total volume. We can see the pH rise as we add sodium hydroxide, slowly at first, followed by faster increases as we get close to our equivalence point volume of 40.0 milliliters added. At the equivalence point, of course, the pH is neutral. Beyond the equivalence point, we'll only be adding sodium hydroxide to a neutral solution, so the pH is determined by the amount of excess hydroxide in the solution. Remember, with a basic solution, you first need to convert the hydroxide concentration to hydronium concentration, and then plug that into the pH formula. We see the pH quickly jump up above 7 initially, and the increase starts to level off as more sodium hydroxide solution is added. Now let's look at a titration curve for a weak acid strong base titration. We'll use a starting concentration of 0.100 molar acetic acid and titrate that with the same concentration sodium hydroxide solution. At the point where no NaOH has been added, of course we just have our acetic acid solution itself. The pH of that can be determined using the methods described for finding the pH of a weak acid in the previous chapter. As expected, this won't be as acidic as the previous example where we used HCl as strong acid, but the pH is still going to be well below 7. As we add sodium hydroxide and before we reach the equivalence point, we will, as with the previous example, have neutralized some of the acid. But what happens if we partially neutralize a weak acid? Well, with acetic acid, that would mean we have some of it converted into its conjugate base, acetate ions, with some acetic acid left over. That combination, as we saw earlier, makes a buffer solution. There are a couple of consequences of this. Of course, the pH doesn't change very quickly before the equivalence point if we have a buffer solution over that range, but there's more we can say about this. Consider that if our equivalence point ends up being 40.0 milliliters of sodium hydroxide added, what exactly did we have halfway to the equivalence point? In other words, when exactly 20.0 milliliters of sodium hydroxide had been added? Well, if you think about it, we would have neutralized exactly half of the acid. That means that half of the starting amount of acetic acid remains unreacted, while the other half has been converted into its conjugate base. If we plug equal concentrations of base and acid into the Henderson-Hasselbalch equation, we end up with just the formula pH equals pKa. So, at this so-called half equivalence point, the pH of the solution must be exactly equal to the pKa of our weak acid. This relationship will be true for any weak acid strong base titration, and does not depend on the starting concentration of either the weak acid or the strong base. Consider also the equivalence point itself. As we saw at the beginning of the chapter, the pH of a strong base weak acid neutralization will be above 7 once the neutralization occurs. Since all of our acetic acid has been converted to its conjugate weak base form, acetate ions, the pH at the equivalence point will be basic, not neutral. It is, however, still determined by the point of sharpest increase on the graph. The shape of a weak acid strong base titration curve will vary somewhat depending on the Ka value of the acid. The higher the Ka value, the more similar it will be to the strong acid strong base case. As we look at the titration of a weaker and weaker acid, several things change. First of all, the starting pH is higher, since we have a weaker acid. Secondly, the pH of the buffer solution formed before reaching the equivalence point will be higher, and if Ka is less than 10 to the minus 7, then the buffer will exist at a pH value above 7, since the conjugate base component will be stronger base than the weak acid is an acid. And finally, the equivalence point will occur at a higher pH for weaker acids, since the weaker an acid, the stronger its conjugate base, which is what's present at the equivalence point. Not only that, but the further the pH is from 7 at the equivalence point, the less steep the increase will be due to the logarithmic nature of the pH scale itself. Let's also consider weak base strong acid titrations, where we start with a weak base and add a strong acid to it over the course of the titration. Just like the case with acid-base titrations, we can determine things like properties or concentration of a base by titrating it with an acid. For the following example, we'll consider the titration of the weak base ammonia with hydrochloric acid, which of course is fully dissociated into hydronium and chloride ions in water. Before we add any HCl to the ammonia, we will, of course, have a solution of a weak base, and hence the pH will be somewhere above 7. For 0.100 molar ammonia, it works out to have a pH of 11.12 when we consider its equilibrium behavior and Kb value. As we add hydrochloric acid, we're going to start neutralizing the ammonia and forming its conjugate acid, which are ammonium ions. Before the equivalence point, however, there will be some ammonia still remaining. This weak base conjugate acid combination is, of course, another buffer solution, and at the half equivalence point, we'll still have the pH equal to the pKa of the conjugate acid in this pair, so in this case, the pKa of the ammonium ions, which is about 9.25. Of course, adding an acid will lower the pH, which is why the graph decreases in pH as we add more of the titrant, as opposed to the previous examples where it increased when we added sodium hydroxide. At the equivalence point, all of the ammonia has been neutralized into its conjugate weak acid, ammonium ions, so we effectively end up with a solution of a weak acid at the equivalence point. As a result, the pH at the equivalence point will be below 7. It is, though, still determined by the point of the fastest decrease in the pH. And of course, beyond the equivalence point, we're just adding a strong acid to a solution with no base remaining, so we get lower and lower pH values with increasing amounts of excess hydronium ions in solution. You may recall from the previous chapter that some acids are polyprotic as opposed to monoprotic. The titrations of these acids with strong bases deserves its own coverage, which we'll address here. Adding a base to a polyprotic acid results in more than one equivalence point. 2 equivalence points for a diprotic acid, 3 for a triprotic acid, and so on. Remember that there are different Ka values for the first, second, and further dissociations. Each equivalence point will occur at a point where the pH increases most rapidly, and they should all be evenly spaced, since they correspond to 1 to 1, 1 to 2, and so on molar ratios between acid and base added. In this diprotic acid strong base titration example, we can see the two equivalence points. Just like with a regular monoprotic weak acid, at the half equivalence points, the pH will equal the pKa for each dissociation. So halfway to the first equivalence point, the pH will be equal to pKa1, the negative log of the Ka for the first dissociation of the acid. Our second half equivalence point also gives us a point where the pH equals, in this case now, pKa2. But remember, this occurs when half of the second dissociation has been neutralized. This is not at half the volume of the second equivalence point, since that's actually where the first equivalence point is. Instead, it's going to be halfway between the first and second equivalence points.